Welcome back, Marauders. This is video 6.5, the quantum mechanical model. In the last video, we learned about Bohr's model of the atom, which does a pretty good job of explaining how the electrons are arranged, but it doesn't explain everything, and we now have models that are a little bit better, mainly the quantum mechanical model. So some things that are not explained by the Bohr model is that really small things like electrons behave like particles and like waves. In the Bohr model, we have those circular orbits, and the electrons just travel around in a circular path, and we know exactly where they are at all times. We find that with really small things that behave like waves and particles, it's impossible to know the exact momentum and the exact location of something like an electron. And then we've also, in class, looked at the photoelectron spectroscopy data, and that data contradicts the Bohr model when you have things other than hydrogen. So we need a better model, and a better model is the quantum mechanical model. This model was developed by Erwin Schrödinger in 1925, and what he did was he used wave functions to describe the movement of an electron in an atom. So he was understanding that electrons behave both as particles and as waves, and he did some really complex math that we're not going to have to understand. But what we do need to understand is the solutions that he came up with, because the solutions he came up with describe locations of space where there's a high probability of finding an electron. So here's two images that kind of compare the two models. So here's Bohr's model. In this Bohr's model, you have the nucleus, and then you have different orbits where the electrons circle around the nucleus, kind of like planets around the sun. And you can compare that to the quantum mechanical model. So you still have the nucleus, but now instead of having these circular orbits, we have this region of space where there's a high probability of finding the electron. So all these little dots represent places where it's possible to find the electrons. Where it's shaded in darker, that's where there's the highest probability of finding electrons. And as the dots get less and less concentrated, that's where there's a lower probability of finding the electrons. So instead of knowing exact locations of the electrons, we have a region of space where it's likely to find one. In Bohr's model, we call these orbits, and in the quantum mechanical model, we call them orbitals. The orbitals have different energy levels, which we sometimes call shells, and they can be numbered, kind of like in Bohr's model. We have the first energy level, or the first shell, where it's in close to the nucleus, it has a small radius. And then getting a little further from the nucleus, we call it 2, and then a little further from the nucleus still, we'd call it 3. So it's kind of similar to the Bohr model in that you have different distances from the nucleus and increasing energy as you go up away from the nucleus. However, it's not like a definite path. It's still a region of space where you're getting further and further from the nucleus. And then the other big difference is that we have these complicated shapes. So like in the last image, I showed you a sphere where there was a high probability of finding the electron, and those are called S-shaped orbitals. And then we have these, which are a little more complicated, the P-shaped orbitals. They look kind of like a dumbbell. There's kind of two areas of high probability on either side of the nucleus, and then it's a lower concentration or lower probability close to the nucleus. The D's get even more complicated, and then the F's get the most complicated. You're not going to have to know the math to draw these graphs. You're not going to have to be able to sketch exactly what the orbitals look like. You should know that the S orbitals are sphere-shaped. You should know the basic shape of a p orbital, but the D's and F's are a little bit more complicated than we're going to need to see. The other thing that you will want to know is that there's only one S orbital. There are 3 different p orbitals. They're kind of oriented in different directions, but all the same shape. The d orbitals come in 5 different types, and the f orbitals have 7 different types. All right, so one way we can kind of organize all this information is in what we call an orbital diagram. So an orbital diagram kind of helps us keep track of all the different places that an electron could be found. So the 1s orbital, this is the lowest energy level orbital and closest to the nucleus. So the 1 is telling us that it's close to the nucleus, and the S is telling us the shape is the sphere shape. So this would look kind of like a circle where you'd have a high probability of finding it somewhere in this circle, and then a lower probability as you go out away from it. The 2s orbital, same shape, it's an S-shaped orbital, but it's a little bit bigger. So it'd be a larger orbital where there's a high probability of finding the electron somewhere in that sphere. And then you get to the 2p orbitals. So the 2p orbitals, remember they're the p-shaped orbitals, so they're kind of the dumbbell shape, looking something like this. And so this would be the region of space where it's likely to find a p orbital. And with the p orbitals, there's 3 different ones. So there's the first one facing maybe that way, second one facing this way, and the third one facing in the other direction. So 3 different p orbitals. They're all kind of the same shape, but they have different orientations, pointing kind of along your x, your y, and your z axes. And then we keep going from there. So 3s would be like a bigger sphere. 3p would be the same shapes as these, but larger, further from the nucleus, and so on into the d's and f's. You probably wouldn't need to draw those. So when we're starting to identify where specific electrons are in particular elements, we have a few rules that we're going to follow. So as electrons are added, they fill the lowest energy level orbitals first. Okay, so on this page that I just showed you, we're always going to start at the bottom. 1s is always the first electron to be filled in. So like in hydrogen atom has just 1 electron, so it's a 1s electron that would be filled in first. The Pauli exclusion principle states that each orbital can hold only 2 electrons. So in this diagram, each box is representing an orbital. And so in each one of these boxes, you can put 2 electrons. When you have 2 electrons, they're going to be spinning in opposite directions. And then Hund's rule says the lowest energy is attained when the maximum number of electrons in the same subshell have the same